Hey guys, welcome back. Another edition of the flipped classroom. So I'm opening up today with a whole bunch of properties of integrals. I'd say take your time here, write these down and see what's going on. The first one we got here is the one we were talking about today in class. If we flip the bounds, it costs us a negative sign. Second one, if we have an integral from a to a, that's as though you're not really going anywhere, right? So that means that area under the curve has to be 0. Next one, we're looking for an integral from a to b of some constant. That you can think of as kind of like just a rectangle, right? Think a constant's just a straight line for your graph. So you have that nice area under the curve. An addition property, if you're adding two functions for an integral, you can split them and look at each of them individually and add them. 2 down, we have the same thing with subtraction. This one I just skipped over here is if there's a constant being multiplied by a function, you could just find the integral of that function over the range and multiply it by c. And the last new one here, if we go from a to c for some integral and then we integrate from c to b, that's the same as if we did just from a to b in the first place. So take your time, write those down, think about them for a second, see what's going on with these, and then we're going to use some of these just moving forward. The 2 new vocab words here that we're using today are indefinite versus definite integrals. So an indefinite integral is something where we don't have bounds, whereas a definite integral is where we have bounds. So there is a defined or a definite answer, whereas indefinite, we don't know the exact answer. So let's solve these quickly. I'm looking at this, and this doesn't look like anything pretty in my eyes right now. But we can rewrite this as 1 over sine of theta times cosine of theta over sine of theta, d theta. We may want to think of these as cosecant theta times, cotangent? And that is actually a nice little trig property if you remember for negative cosecant. But since it's indefinite, you have to remember your plus c's at the end. So we've done a lot of indefinite integrals, and we've done some definite, but just to do another quick one with us here, you take the antiderivative as you normally would. We now need to evaluate from 0 to 3. So if we plug that 3 in, that's 81/4 minus 3 times 9 is 27. We're subtracting 0 from all of that. When we go through and do this, it's going to end up being negative 6 3/4. So a lot of stuff hopefully we've seen before. The big thing is understanding the difference between indefinite versus definite. And then one new style here today. So of course we have all these things that we've been doing, but we also sometimes want to use these in the real world. So there are some applications we can look at. So any real world application tends to be this physics-based stuff. So of course it's going to be some particle moving across a line, so that its velocity is given by this equation in meters per second. It says find the displacement of the particle during this time period from 1 to 4. So displacement is super easy to find. If we're doing displacement of any particle, all it is you take it over its range. So we're integrating from 1 to 4, the velocity function, and then I put dt at the end, sorry. So we're doing 1 to 4, our velocity here. If I write the equation out, we take our antiderivative, from 1 to 4. We put these numbers in, and let's see. I wrote these out somewhere so I'm not killing myself. What's this? 64 thirds minus, this is going to be 8 minus 24. And we're subtracting from all of this the 1 values here when we're putting in ones. A third, a minus 1/2, minus 6. Be careful with your arithmetic here. This is the number one mistake. This, if you get here on my tests or quizzes, this is like 9 out of 10 points if you're getting here. Then you got to actually be able to go through, plug all these in, and see that we're getting negative 9/2, and this is going to be meters. So what this means in terms of this particle moving context is from 1 to 4 seconds, the particle in that time period has moved back 9/2 of a meter. So 4.5 meters. So displacement, easy. The distance traveled could be a little harder. So distance traveled, we have to think if you're moving forward and backwards, right? Displacement, like if you run around a track, your displacement, if you're back at the start, would be 0. It's as though you haven't moved. However, your distance traveled, if you go around a track, you have to count, it's that whole 1/4 mile. So we have to do something a little different here. We've got to know when are we moving forward versus when are we moving backwards. So in order to get here, you need to take your velocity and set it equal to 0. So if we're solving this equation, equal to 0, a quick factorization. What's that, t plus 2? So at 3 and negative 2 seconds. Since negative 2 seconds isn't really occurring, all we have to think about is the 3-second iteration of this. So if we want to find the total distance traveled here, I need to have 2 integrals from 1 to 3 for our velocity and from 3 to 4 for our velocity. If we're going through and doing this, let's see. Oh, perfect. Hopefully we get a 10-second countdown.
At this time, we're in a hold in your classroom, clearing the halls, or students remain in your classroom until the all clear sounds. Teachers close and lock your classroom door. Take attendance. Thank you.
So we're setting up these integrals here from 1 to 3 and from 3 to 4. Since we've split it up here, knowing one of these is 0, or 3 is where it's at 0, one of these will be negative, the other one will be positive, and we need to take just the positive version of each. So we already know the antiderivative. It's the same for each of these, just like we did above. If you're going through and doing this, I'm not going to do all the arithmetic out. I have it off on a scrap piece of paper. We should have negative 22/3 here, and we should have, what's this one over here? 17/6. Go through, work on your fractions. They may be gross. But since we wanted the total distance traveled, since this one's negative, what we really should have done from the beginning was think all of this needed to be within some like absolute value of what we're doing. So really what we want is 22/3 plus 17/6, which should come to 61/6 of a meter. So just over 10 meters. Okay. Homework that we're going to be looking at tomorrow. We're in 5.4. 21 to 43 are a bunch of definite integrals. 59 and 60 are some application ones like this. This may be too much, but I gave us just odds to look at. So start looking at maybe 1 or 2 of these, make sure we're getting the gist of it, and I'll see everyone tomorrow.